Check 1, 2. We're all ready to go. Okay.
Seriously? It was really reasonable like a week ago. I thought I was going to come and wear my sweatshirt and go skateboarding.
Where's Frankie up here too? You ready? Yeah, come on up. All right, thank you all for joining us tonight. I think we're going to get started here in a few minutes, but hopefully we're not going to get snowed in, but hey, we'll have a good time, right? So we're live streaming this right now on YouTube on the MetaMask channel. We're also going to be recording all the talks as well, so that we can publish these later. For all the presenters on this list, if you do not have either the DisplayPort for Mac or HDMI, please let me know now. But I think we're all good there, if not. And if you do have a Mac as well, if you could record your presentation on locally with just QuickTime, it'd be great. Make it a little easier to put this all together. All right. So to kick off, actually, first and foremost, let me thank Galvanize, who is hosting us here tonight. So thank you very much. And so for the MetaMask teams, can all the MetaMask folks please stand up? They did a hell of a great job, especially this one right here. Frankie, organizing this event. And everybody here from the IPFS crew as well, so thank you all. So we got a couple here. Right. All right, so first and foremost, we've got FlySwatter, who's going to give us a nice overview of Ethereum in general. So I'm sure most of you are probably going to be pretty familiar with Ethereum, but it's good to always have a nice little refresher and overview. So Dan, come on up.
Thank you, Kenny. Thanks, everybody. This is a really exciting thing to be a part of. I can't wait to see all the talks. I'm here to get people acquainted with the basics who might not otherwise be. So I'm just going to be covering the basics. So just to get an idea, like, who knows what a Merkle tree is? Or sorry, who doesn't? So I know who I'm talking to. You know, like, yeah, this is for you. Okay, maybe it's one person. Maybe there's some shy people. I'm going to try to go kind of swiftly. I'm going to try to do this as lovingly, smoothly as possible. And hopefully you'll come away with a better understanding of some of the fundamental pieces that this whole thing's made out of. Let me clip this on. Never mind. All right, so the first thing I'm going to give you is hashes, okay? We might as well call tonight Hash Fest because everything we're doing is like built on these cryptographic hashes. Yeah, what? Hash bash? Yeah, if we do this again next year, we should call it Hash Bash. A hash is just it's a function. You give it some data, and it gives you out some random data of a consistent length. So you can see here I've got hello Seattle, and then hello Seattle with an exclamation mark, and then they give you two totally different numbers, right? So you can see that a small difference gives you a totally different output. It always gives you the same length output, and it should be very unlikely that two inputs ever give you the same output. So that's like a kind of interesting thing. And what's cool about that is once you have a hash of a file, you can pretty easily, you could pass that to someone. You could say, hey, this is my social security number's hash or something, and then you could prove if you ever had it, right? So hashes let you do some cool things regarding proving that you have some information that somebody else hashed, okay? Now, those get combined. When you take a hash of a couple other things, you can do something cool called the Merkle tree, right? So let's say we've got two different files. We could hash them into a hash, and then we could bundle that with another hash, and now we've got a hash of that. And that data structure has some interesting properties. For example, so this is one Merkle tree here. If we change one file here, and I think this metaphor is pretty cool. I haven't seen anyone do the color mixing, right? Color mixing is a pretty good metaphor for it, because you get out something that you could only get from the inputs, but you can't easily figure out what got you to that, right? Okay, so let's say we change one of these input colors, right? We change one file, and you can see that changes what that first color gets mixed into, which changes the resulting one. So if you just have the root hash, if somebody says, oh, here's my Merkle tree, here's the root hash, you can know, oh, okay, so I can prove if I ever have their whole hard drive. But then if they say, here's my updated thing, you can know something changed. And if they give you basically just up that branch, then you could actually have all the changes, and you could prove that the only things that changed were those things, right? Let's say you had all of these. and then you get that one new file. You can just go up there. You're like, okay, let me hash that. Yeah, it does create that. I can hash that, and you get the new result. And that's called a Merkle proof. Okay, so what it lets you do is it's a very cheap way to validate that a small piece of data is in a big data set. And this is really valuable when you're in a distributed network. We're like sharing some kind of database together, and I want to give you something that you can trust. So I want to give you as little as possible to like establish that trust, right? And that's kind of what a root hash is good for. There was a recent announcement like Apple's going to use their new file system is going to be based on Merkle proofs because they'll be able to tell as soon as a single file is corrupted, right? It's like if you can't prove the root hash, then you know a file's wrong, and then you can just go through, figure out exactly which one. So it's a really useful data structure. What else can we do with that? Oh, well, if you're a software developer, you're familiar with Git, and Git is just using these same Merkle trees. You may have not noticed you were using Merkle trees, but basically you've got all the files in your project, and when you change one, Git just saves that one and then gives you a new commit, and then you've got that commit hash, and then you can always check out a hash, and you can check out a hash at a different point in history, and it gives you these really cool properties. And you'll always hear programmers say, like, I just wish more people could have Git. I wish lawyers had Git. We could just have like version control the legal system, because you could see the one-line difference. Here's what I want. It's just that much different, but it's got a different root, and so you can prove that I'm only changing one line. Anyway, so Git's great. Git's very valuable, but that's not all you can do with Merkle trees. Okay, blockchains are another thing that use this data structure, where you're taking a file, you're taking a hash of it, and then you maybe just want to add another file to it. So you just now take the hash of that new file with your previous root, you get a new root. And so now what you can do is you can prove that this file came after that. Okay, and so now you've got this like kind of causality, and so you can always just kind of add something in, and then you get a new root. So as long as you've got a good way of getting that root, you have a good way of establishing trust all the way down. You can prove the entire order of history on this data structure. So this could be a hard drive, this could be a shared, to-do list at home, whatever that is. Right? The point is you add some data, you hash it together, and you keep moving forward, and you get this ordinality. To be fair, that's kind of only one half of what people call blockchains. Okay, that's like the block part. But I'll get to the consensus layer in a second, which is a fun thing. So Bitcoin is basically just that as a data structure, right? We take a list of transactions and we hash them with the original root. And what's cool about this is now we always know that these transactions happened in a certain order. And that's why Bitcoin, they say, solves the double spend problem. The problem that I could like tell two people that I'm giving them the same $50 and then them both saying, oh, I guess I got paid. We have to have a single source of truth to establish a kind of shared money system. And so that's kind of what Bitcoin established. They say, you're saying, okay, if we have blocks of transactions at a time, we know for certain these happened in that order. Okay, I'm gonna try to summarize this quickly. So when you've got this data structure with a lot of people, the hardest part is establishing what is that root hash that I'm going to trust. I could just email it to you and you could just trust me, but that doesn't sound like very decentralized. I could just get corrupt. So how do we come up with a method of who gets to add the next block, who gets to add the next series of transactions to this ever-growing database? And what Bitcoin proposed is to have a consensus protocol. We've got a whole bunch of people that are basically racing to get to be the one who adds the next block to the blockchain. So Bitcoin does that with proof of work. So it's basically a really hard computer problem. I'm going to tell you, I'm not going to really talk about nonce because I'm trying to keep this quick. We have some amazing talks. But basically computers racing it's just a one CPU, one vote. And they're just trying to get the privilege of adding that next block, which gets to decide the order of all the transactions, which is a powerful thing. So part of the point of these distributed systems is preventing any one source of power from getting to decide the final order, because that would just be too much power. The miners, of course, get an incentive to do this. Every time a miner successfully makes a correct block, they get some bitcoins, or in Ether they get some Ether rewards. Okay, so what's Ether? Ether's the same thing, but instead of a list of transactions at a time, we're taking a whole computer's state. So it's this whole virtual computer space, and then in one of these blocks is a series of transactions. They're like computer operations, like Like you sent an email, or you sent some money from one person to another, or you voted, or you finished a crowd sale. All these things are things a computer might do. And so all of those things would be state changes in a block. Then we get a hash, and then we start again. And it's this continuous process. So Ethereum's basically a virtual machine on a blockchain. A single block has a lot of things. It's got a timestamp, a hash, the hash of its parent. The important thing, though, is the list of transactions. So a transaction, each interaction you have with the blockchain, it's from you. You cryptographically sign it. You're the only person who can control your account. And then you can interact with these little programs that live on the blockchain called smart contracts. And every time you interact with the blockchain, also, you have to spend a little bit of ether to incentivize the miners on it. And it prevents you from just spamming the network and bringing the whole thing down. Ideally, making the computer do things is priced in such a way that they don't want to harass it. So here's just some cool visualizations made by Kumabis over here. So here we've got the virtual machine state. Here on the edges, we've got user accounts. And here's some contracts inside Ethereumville, okay? So you can, of course, send some ether from one person to another. You could also send some ether or call a method on a contract inside the machine. The contracts can also have side effects. So you could call, for example, you could have a bank account thing where you turn up your kid's spending limit, and then maybe their allowance, and then it sends to them, for example. Or there could be complex chain reactions. Maybe you change your voting preferences, and your legislation gets adjusted accordingly. You can also do things with these contracts. You can write whatever arbitrary code you want. So you can have complicated rules, like maybe several people's approval is required to do something. When you create one of these contracts, you literally define what it does. The way you create it is you just send a transaction with no recipient. And then the data that you put in that transaction becomes code in the virtual machine. So this becomes a program, and it'll just run whatever you want. Basically in public, totally transparently, and it'll just sit there waiting for you to do stuff with it. What are people doing with it? They're doing all sorts of cool things that require a public computer that's transparent and kind of lives in a shared space. It's people crowdfunding, working on governance, prediction markets, accounting, art ownership, exchanges, gambling, of course, there's scams, scams a dime a dozen. In this space this early, get familiar with those and avoid them. But then there's also really cool generous things. Yeah, peer-to-peer lending. There's as this ecosystem matures, it's got a lot of cool potential, and a lot of people are pretty excited about it. And that's my intro for this. Thank you.
Thanks, Dan. So up next we have Juan. Juan is the founder of IPFS. Juan's talk today is going to be called Enter the Merkle Chorus. Yeah? Forest?
Yeah.
Yes.
Merkle trees, Merkle forest.
Nice. Okay. So if you want to go ahead and clip this on, you can do that, or however you want to do it.
Yeah.
Okay. I'll just put that up here.
Can you hear me? Is this good? I don't know if... Okay, great. Let's see.
The audio is not being amplified, it's just being recorded.
Okay, got it. Anyone know how to enter DND on OS X? I don't want it to like...
Oh, yeah. You press that little notifications bar on the top right.
Yeah.
And then scroll to the top. It's like above where it's...
Oh, because that's totally obvious. Ooh, we need mirroring. Yeah. Sweet. That's good. That might be good. I think I may be able to swing it, but just in case, because I don't know the driving. Let me grab my. That power cord won't work. The cord. Yeah, but it's like a USB-C. You know. Like. All right, I'm ready. Thank you for filling that time, and thank you also for coming in the day of the Super Bowl. It occurred to us, to several of us, I'm like, oh yeah, this is a clash of conflict. Cool. So my name is Juan. I started the IPFS project, and I am here to talk to you not about IPFS specifically, but really about IPLD, which is a format that has come out of IPFS. And this is really the heart of the IPFS project or the ecosystem. Everything else we do is a lot of hard work to make IPLD work really, really well with a whole bunch of different data structures in a whole bunch of different contexts and so on. And so hopefully after tonight, this is a new take on explaining IPLD. You'll kind of get a better sense of what IPFS is about. Because IPFS, despite the FS moniker in the name, it's not truly about files. It's just about content and data moving. And so it's a new kind of file system where you can also call the web a file system if you wanted to. But it centers on Merkle trees, as was explained just before. So thankfully, I don't have to go and explain Merkle trees, so that gives me more time. I'm also going to set a timer so that I don't run over. Yeah, I mean, I don't want to. Careful with that. I've been known to take a million years, so cool. All right. This will go off in 20 minutes. All right, cool. So the talk is titled Enter the Merkle Forest. And, this is a whole bunch of the projects that have spun out of IPFS. And so the middle one is Protocol Labs, a company that we're building to fund the development of all this stuff and more. There's probably more projects that are not seen here. Multi-formats, IPLD, and libp2p all came out of IPFS. So did Filecoin, sort of, but that's a whole other story. These are things that we think are extremely valuable and useful to a lot of other systems and projects, and that's why we work hard to make them independent projects that are not IPFS specific and that can be used separately, that you can use in your own systems. So tonight I'll talk about IPLD. So I won't give you much about IPFS, but luckily there's like dozens of videos online of me explaining it. So if you really were here for that, I can give you some cool links. So the IPFS stack, and so IPFS is this large distributed system for moving around a bunch of hash-linked data. Let's just say that's what it is. It decomposes into this stack where at the very bottom there's this libp2p thing that is all about peer-to-peer systems and peer-to-peer magic to get to solve problems of how do you get two devices talking to each other across a variety of contexts or situations, right? So if this room right now lost internet connectivity, like connectivity to the rest of the world, we should be able to continue working with each other. Our applications should still be able to work. The stuff and data that's in this computer and programs that are in this computer should be able to talk to the programs and data in your computers. If we were working on say a chat room like Slack or working on a Google Doc or something like that, we should be able to continue working even though our connectivity to the rest of the world stopped. And so IPFS is a system that enables that kind of work, and it does it by combining IPLD, which gives you hash links and content addressing, and layers all of that on top of libp2p, where libp2p is this whole bunch of grab bag of protocols to make it easy to do that connectivity, right? So leveraging hardware and software that's written for like specific networking, something like use Bluetooth or use audio or a whole bunch of like esoteric protocols that would allow our computers to find each other, would allow our computers to transmit data to each other, use Wi-Fi and find each other without any internet, introducer whatsoever, right? So libp2p does all that heavy lifting, all the peer-to-peer magic, and it's kind of abstracted out so that anyone can use it, again, for any project. And so what IPLD is about is, we call them Merkle DAG. It's not a great name. DAGs, unfortunately, we're kind of screwed in the nomenclature world. Trees sound much nicer, but calling it a Merkle tree is not exactly correct, but we can go with tree because it's a nice metaphor. And everything else, all the IPFS file-specific stuff, all the application stuff, all of that layers on top of IPLD. So you get a structure that looks like this, where all the libp2p stuff is like this madness around doing heavy lifting on very case-specific stuff that's kind of abstracted away. And then you layer this really nice, simple interface of doing hash links on data, and you get the assumption that you should be able to create and resolve hash links. And on top of that, you can build a ton of other stuff. Like you can build a bunch of different kinds of applications on top. And so this is what we like to call, this is kind of a thin waist protocol, right? Like it's a thin waist model where you separate your whole construction into pieces where at the bottom, a whole bunch of things can evolve and new things can be introduced and so on without meaning any change to the applications on top. So this comes from IP. So when you think about the IP protocol, it's a thin waist protocol because IP addresses and IP schemes could remain the same for 40 or so years and counting. And everything else can be separate, right? Like the underlying protocols underneath, whether you're communicating over radio or over Ethernet or whatever, all of that can change. And applications on top, like Google Docs or Slack or your web browser or whatever, all of that can change on top. And so similarly, we have a design construction that gives you that nice thin waist that we can all agree on, and then make applications that can work over any kind of networking. So I'll give you some intuition for what IPLD is. And so when you think about IPFS, and you add some files to IPFS, this is kind of what the command line version of IPFS looks like. You add a bunch of files, and you get this like stream of output that says like added some huge, horrible hash, and then some file path, right? And you get, this is adding a whole directory. And so what's going on here is that IPFS is looking at your normal file system, like your POSIX-y, Unix-y file system, and reading a bunch of files and reading directories, and then constructing this huge graph and using hash links to connect all of those pieces together. So it works, you get something like this. So this is I think this is the corresponding graph for that. And so you get something that looks like this. Notice, by the way, that there's deduplication going on, that foo.jpg has some of the same content as tree and cosmos.jpg. And so because you're using hash links, you can just start deduplicating a ton of content. So that's one cool thing. The other cool thing is that, as we heard before, all of these things are secure links. You can give somebody this hash, and they can go and ask the network for the content matching that hash. And you can, under standard security assumptions, you can assume that nobody can forge that content, right? Like nobody has the computational power to be able to invert a hash function to something else so far. Depends on which hash function you pick, depends on whether there are attacks and so on. This is a big caveat there, but that caveat is the same as, any kind of crypto anyway. So if that's broken, pretty much everything else is broken too. And so there's a nice facility also in IPFS because it aims to be this long-term project that we can even roll up our hash function. So if we someday discover that SHA-2 is broken, we can move to SHA-3. And if that breaks, we can figure out what to do then. And I'll describe how it works. So, as we were discussing before, this is a Merkle tree, right? And Ethereum is a Merkle tree. And turns out there's a whole bunch of other things that are Merkle trees. So this is Plan 9, old OS. Its file system was a Merkle tree. BitTorrent, it's a little, I like to call it a Merkle shrub because it's like a really, really shallow Merkle tree. Git is this hugely long Merkle tree where it has huge commit graphs and so on. And then Bitcoin and Ethereum are these massive Merkle trees, right? Like just enormous, like hundreds of thousands of nodes and growing, right? And so it's this really beautiful construction where all of these things, all of these things are distributed, authenticated, hash-linked data structures. So distributed because you can move them around across a bunch of computers, and authenticated because you can check that the data is actually correct. You can check the integrity. You can check that it's truly the data you were meant to get, and so on, right? So if I communicate a hash to you, you can, again, ask anybody else in the room for the data that matches that hash, and you're good. And the cool thing about Merkle trees is because there's this recursive construction, I just have to give you the root. And now you can ask everyone for the next node, and then that node contains links, and you can fetch the rest, and so on. So I can, in a very compact representation, like in SHA-256, 256 bits, tell you and uniquely identify pretty much as much content as I want, as I have generated in the past and distributed to the network. So this awesome compression function in a way. And so these distributed authenticated hash-linked data structures, so hash-linked is sort of part of authenticated, but I want to express it, pull it out as part of the definition because there's other ways of doing authentication, so digital signatures and so on. So you can think of IPFS as a Merkle forest. So instead of saying we have one huge, massive Merkle tree, like, say, Bitcoin or Ethereum and so on, IPFS is about creating a whole bunch of different Merkle trees and being able to resolve through all of them. So if content is on Git, awesome. If content is on Bitcoin or Ethereum or whatever, we should be able to resolve through it and find it. And you're like, whoa, that sounds kind of crazy. How could I link from a Bitcoin node to, from a Bitcoin blockchain to the Ethereum blockchain? If I use the same hash, won't that kind of collide? Like, that's not a non-trivial thing to do. And so that's what IPLD is for. It's about allowing linking across these different kinds of data structures. So we call it the Merkle forest. The definition we're going with at the moment is a common hash chain format for distributed data structures. And so it allows systems like these to interoperate. And today we have support for a number of these already in IPFS. It's not merged into master. It's in the next upcoming release. But the cool thing is you will be able to make an Ethereum transaction and include a link to Git and be able to resolve through transparently over IPFS. So you'll be able to have a nice path notation and take the transaction of Ethereum and walk down it, find the Git link, and you keep going down and refer specifically to all the underlying content. So it's a little subtle of why that's really cool, but it's like having a native API to every single one of these systems without having any of the code for those systems and having it all work. It's kind of like the web, but for hash-linked data structures. And it's also compatible with the web, so you can use it from any web browser or your terminal. How does it work? When you break it down, the properties of this thing is that you have a thing that gives you Merkle links or hash links. These are secure and immutable. And you have a path notation for how do you traverse through this graph. And you have these we call them universable or nestable URIs, where again these paths are just as URIs that you can combine. And then you have a whole bunch of different serialization formats that are what gives you access to each of those different data structures. So you would have a different format for Bitcoin, and a different format for Ethereum, and a different format for Git, and so on. And what that format gives you is the notion of how do you traverse through that data structure, right? So if you find a Git object, inside of it you see hashes, but those hashes from within Git normally just mean other Git objects. They don't mean Ethereum objects. So you need a notion of how to teach IPFS or IPLD enabled things to understand that format and understand what are the hashes and understand how to resolve through. And once you have that, which is actually quite small, it's a very simple interface. You write 2 functions. After you have that, you can resolve through this entire new data structure and plug it into the rest of the system. Little side note here is that we're thinking about and exploring how to write all of those things in WebAssembly. So write them in JavaScript, compile them down to WebAssembly, and now you have them running on every architecture you want. And the last thing I'll mention is that because we have things like JSON and so on, you want to canonicalize the data so that it's hashing safe. You could have the same JSON data structure, and based on how you serialized it, you may end up with different hashes, which is silly. The components of the IPLD project are CID, which is a content identifier. I'll talk about it today. It's a format for how you structure the hash links. There's a data model, which is basically just, you can think of it as like the JSON data model or like an extended JSON data model where you basically have strings, integers, floats. I guess JSON doesn't have ints, but it's like the very basic things, maps, lists, and so on. And out of that, you build everything else. And then you have, again, those serialization formats I described. We have tools and libraries that you can use to work all this stuff. And then we have selectors and transformations. I won't talk about these because these are kind of complicated and assume some understanding of the thing. But I'll just describe what they are very quickly. With IPLD, again, you have these huge graphs of stuff, or like these huge Merkle trees. A selector is an expression, a path that allows you to sub-select not an individual node, as a path would give you, but a subgraph, like an entire subgraph. And that is really useful to be able to express to other peers, like, oh, I'm not interested in the whole thing, but can you give me like this sub-selection? Or, oh, I really want to download the very first parts of this huge file so I can stream it right into the browser and start playing a video or something. So that's what selectors are for. Transformations is what happens when you add computation to the mix. When you say, here's a graph, and I want to turn it into another graph, and so here's some code that gives you, that when you apply it onto this graph, gives you some other graph. And you can then take that and transform graphs into others. This is still ongoing work. The selector is close to done. Transformations are just beginning. But you don't need that to already be useful. So everything that I'll talk about today is already good and you can rely on. So the CIDs thing turned out to be incredibly important. How you create that format to link between these data structures such that it's tiny and flexible for the future is where a lot of the magic of IPLD is hidden. And it actually took us a while to get to it. I'll give you a little bit of background on that. So I already talked about how IPFS has the ability to roll to different hash functions. We do that with the thing we call multi-hash. And so this is part of the multi-formats project that I described at the beginning. We have another thing. These are just different formats for making self-describing values. So the idea is that if you see some value somewhere, that should tell you what it is on its own. And how you do that in a very tiny, compact way, such that it's binary packed, so that people don't complain about how much size it takes or whatever, is important. And what you get out of it, like the value of doing this, is that when you see a hash, it will tell you, oh, I'm a SHA-256 hash, or oh, I'm a Blake2 hash, and so on, which allows you to understand what you need to do with that value. I'll give you an example. Let's take 4 outputs of different hash functions, and these are all outputs of the exact same value. And if you were given these values, you'd be like, great, I have no idea what to do with them because I don't know what hash function it even is. They're all the same length, so normally what people do is say if it's 256 bits, it's probably SHA-256. If it's 512 bits, it's probably SHA-256. Oh, but wait, SHA-3, it's also 512 bits, or whatever. So that's annoying. So why didn't the person that gave you the values, why didn't they just add a little bit of information right at the beginning of the value so that you know what it is? The reason this turns out to be important is that systems like Git and so on use hashes, and now it's all of this work has been done on these hashes, and SHA-1 is going to break. Like it's already broken. Everyone's known that they need to move to SHA-2. And yet we still use those hashes for a lot of stuff. And we rely on the security of that SHA-1 hash. And if so much of the Git code depends on those hashes being a specific size, 160 bits, and like so much stuff just creates and allocates buffers that are just that length. So that if you suddenly said, great, let's use SHA-2 and bump it up to 256 bits, so much code around the world would just break. And you'd have to do this enormous amount of effort. And so what's likely to happen is that Git is going to say, no. We shouldn't jump up to 256 bits of security. If we're going to jump to SHA-2, we'll probably have to clip the hash to 160 bits and just roll with that. And that is just an artifact of them not giving you the length of the hash ahead of time. And so looking at this and being frustrated, we made the format called multi-hash that tells you how long the thing is, and that tells you what hash function it's coming from. So that if a system uses these things, they know that these hashes may be longer in the future, that we might roll to a much stronger hash function in the future that may be, I don't know, 10, 24 bits or whatever. Or that it's a different hash function altogether. Or maybe we figure out how to make super secure hash functions that are only 100 bits, and we say, oh, why are we wasting all this space? That won't happen, but anyway. So yeah, multi-hash is this very trivial, simple format that just tells you what the function is, tells you the length of the value, and the digest. It's self-describing. There's no assumptions, no lock-in to anything, and so on. So yeah, that means you have to maintain a table of agreement on like what a code means, right? Like 11 in hex means SHA-1, and so on. But this turns out to be not that much work, and all of our distributed systems already rely on tables like this, right? So if you want to speak IP or TCP or whatever, you're already using tables. So it's not a big deal. There's a whole bunch of implementations of multi-hash. There's more, but I haven't taken another screenshot in a while. And there's a few other multi-formats protocols that you don't really need to know that much about them. Multibase is for allowing you to use multiple different kinds of encodings. And multicodec allows you to use different serialization formats. And so these are the three that we use in CID and IPLD. This is the example of multibase, just another table that tells you what you're doing. Like if you have ever seen some base encoded thing, and you're like, what is that? Is that base 64? Is that base 32? You basically have to figure it out. And like programs that guess and are wrong or use a different alphabet, like just it all gets garbled and wrong. So why don't we just have a nice code that tells you what it is? This is a interesting, tricky problem where each specific code also happens to be a byte that fits within the alphabet of that encoding, so that it just all nicely works. So what a CID is a combination of these three pieces: the multi-hash, multi-base to allow the different bases, and multicodec to allow different serialization formats to be invoked. This is basically it. Like it's a very simple format that just has like the multi-base prefix, a version for the CID, because we may want to change this in the future, and like if we change it, and like we already went from v0 to v1, so like things may change, and you always need a version. Then you have like this multi-codec packed code that tells you, oh, this is a get object. Oh, this is an Ethereum object. Oh, this is a get object, and so on. And then you have the hash in the end. And so what that gives you is the ability to, just in one simple hash value, understand what you're linking to, understand the hash function you're supposed to verify it with, understand just the string thing that you're looking at, which base is that in. Bitcoin loves to use base 58, and like that set a precedent for everyone trying to use base 58 for everything. But it turns out to be slow. Or browsers aren't, we just ran into this. I wrote like a very long email today about how you can, if you go straight into the browser and you want to use a base 58 hash as an origin, for example, for a browser, that breaks because browsers assume that the origins are case insensitive. So now you can have two different hashes pretending to be the same origin. And you're like, what? So you have to now turn all of those things into base 32 or 16 or whatever. And the fact that we have multi-base already saved our asses there. Cool. So does this, at the end of the day, this is just a format for the value of a link. For if your data structure started with these things, then you can point across them, right? So I could take a get object, and I could write this hash in there, and now it can point to an Ethereum hash, or now it can point to a Bitcoin hash. And so that's the value there. There is a problem of like, oh, wait, you can't rewrite Git. You can't rewrite Ethereum. And so you need to understand that in those data structures, they might have native links between objects of its same kind, and they won't be formatted like this, unfortunately. That's just a reality in that we can't go back and ask everyone, like, hold up, change these blockchains, rehash everything, just because we think you should. Nobody will do it. So we need formats that are understanding that how you can resolve through. And it turns out to be a pretty easy problem because whenever you have an Ethereum hash on its own, you're usually in an Ethereum context. So you can assume that the thing that is not a CID is probably just an Ethereum hash. Same with Git, same with everything else. Oh, man. That's 20 minutes. So I will give you a quick example in code, and then I'll shut up and let other people speak. So the basic idea is that we were driving for something like this, where whether it's a command line or code or whatever, you can grab an object. This could be whatever you want, and you can marshal it. Whatever. Here I left out which serialization format, but suppose that this is just JSON-powered IPLD. You have some value, and then you can get its hash. This will be CAD. This example is not super up to date. This long token will be prefixed with this other CAD stuff, and then from there you can do things. You have now created an object in the IPLD world. You should be able to refer to this as well. So you can create another object, like you have hello and you have world, and you have now two different objects, two different hashes refer to that object, and now we can write a third object that points to those two. You have a third object and has a files array in it, and one object here is a link. This is how we structure links from one JSON IPLD object to another JSON IPLD object, and you have the whole value there. And when you get the data of this thing. So this is the hash of that third object. So what's going on here is that these are hash links. And you get a structure that looks like that at the bottom, right? Like you have the object 3 pointing to the first two objects that I showed you. Given this, you can add all these three things to a system like IPFS or anything else that uses IPLD. And you can resolve each one of them, right? You can resolve the first one and get the data. You can resolve the second one and get that data. And then you can do this nice thinking. So by the way, here, one cool thing of the path notation in IPLD is that you can traverse through these objects. Not only do you get each chunk of data, but you actually can use the data model, JSON-style data model, to traverse through and get pieces out, which will be really cool when you see some of the blockchain stuff. Like you can go into a transaction and just pull out one of the values really nicely. And it gives you effectively a JSON API for free. And so you just add, append to the end of the hash the path notation that you would want. But now the cool thing is once you think about three objects, you can resolve it and get that data. You can resolve it and get whatever the array is and so on. And what you can start doing is you can traverse through transparently, right? So you have the third object, say /file/0, would hit the first object, and that was native resolution. So what happened here was that it went to the third object, looked at the link, and said, great, let's resolve this, and go and fetch the second link. So that could have been a network call right there. So this could have gone out to the rest of the world, fetched stuff, and returned it to you. When that happens and so on, it's all very system dependent. But the cool thing is that you can start treating data in this huge data structures as just being ever present, and you just have some nice path notation through it. And it doesn't really matter how it's chunked underneath. You can still access all of it through this nice, very nice uniform path notation, whether it's in Git, whether it's in Ethereum, whether it's just JSON, whatever. And the cool thing is that you can then create things like a file system, really trivially, and say, suppose that we had a function called catfile, and we're going to give it a link. And what it's going to do is going to resolve the link first. It's going to look inside of it, and if it has some data, start a string. And then it's going to go over each of its underlying files and treat those as sub-files, right? And say treat those three objects as files and say that the content of the content of the file described by object 1 is just going to be the data. The content of the file described by object 2 is just going to be the data. And the content of object 3 is going to be data if it has any, and concatenating the two things that it points to. So just with this, if I catfile the first one, I just get hello. If I catfile the second, I get world. And if I catfile the third, I get the concatenation of those two things. So this, in 5 lines of code, you have a file system that it gives you sharding of files, right? And can take huge things and break them up into pieces and concatenate them over time. So you can do these things in code above IPLD, or you can start thinking about them in terms of transformations underneath the hood. I won't give you more examples, I think, because I've been going for a while. But that's other people will, and that's it. Let's enter the Merkle forest. Thank you. We have a whole chat application built on top of this that gives you all the objects are just in IPLD. Thank you.
All right, so up next we have Kumavis, who is the founder of MetaMask, yeah? Yeah. So get him a, yeah. Grab that on.
Whoops. The boffin. Thank you. Thank you. Cool. This is going to be a very short talk. It's basically going to be me dragging a highlighter over certain parts of what Juan just said. Ethereum on IPFS. So yeah, we kind of dug around inside the internals of IPFS and IPLD and how all that works. And so how can we take an application that wasn't built to work on IPFS and sort of map it onto IPFS and see that that actually works pretty well. So yeah, Ethereum loves IPFS. We were hoping to have these stickers for you, but they never showed up. So what's a blockchain? It's a combination of a couple things. One, you have a peer-to-peer network. You have a consensus algorithm. You have some historical log, and you have which in aggregate gives you the current state. And both the historical log and the current state, they're hash-linked data. So you've seen some graphs already. It looks a bit like this. So IPFS is a peer-to-peer network that serves hash-linked data. And so IPFS, or Ethereum on IPFS, is a peer-to-peer network where you get your hash-linked data for the state and the history, and then you just layer your consensus algorithm on top for you to resolve what's the current head, where's the current state. So I'm going to talk very briefly on IPLD resolvers, and then you're going to get more of a deep dive in the next talk. So this is my possibly fictitious history of IPFS and looking up data on IPFS. First, you look it up by a hash, and you get data. And they're like, well, it makes more sense to be able to use any kind of hash to look up your data, and then using any kind of hash to look up any kind of data format. So then the resolvers, when we specify the format, we can use these resolvers to look inside that data. We're getting some binary data blob, and you can pull out some specific information, or you can pick out a link to something else. And we can use human-readable names. So if you have your identifier for your Ethereum block, you could grab the number of that block, or the miner, the validator that created that block. And then you can keep going. You can say, like, I want to look at inside the state, the sort of snapshot of the state at that block, and I want to look inside an address, and I want to get the balance of the user at that. Or you could look inside, if it's a smart contract at that address, you can dig into that smart contract and get some value inside its storage at some key. And so while we had to build an Ethereum-specific IPLD resolver, when you look up that data, it will auto-generate a Merkle proof that value is correct, and without the system having to really understand any semantics of Ethereum, that this is a smart contract and it has storage and all that stuff. We just use the IPLD to walk you through those data blobs to other data blobs. So that was reading static data about the blockchain, but there's a lot more going on. How do you take actions in the network? So libp2p is part of the networking stack used by IPFS, and they have a feature somewhere between development and production called Global PubSub, and it lets you basically globally subscribe to topics on the network or publish on those topics. So utilizing that, you as a client, you could just subscribe to incoming blocks, and every time the network knows about a new block, you get that new block, and then you can sign your transactions and publish on that topic that there's a new signed transaction. As a validator, as a miner, you'd want to, of course, you want to also know about new blocks, but you'd also want to listen for those new signed transactions that you'd want to put inside your block, the block that you're mining, and then you can publish the blocks that you've mined on that topic. And then we can start experimenting with other things. You didn't talk about IPNS too much, but you can, IPFS is all mutable or immutable links, right? So they're all static. IPNS lets you basically publish an updated value at some name, and that updated value or that mutable value is just pointing to another immutable reference, and then you could walk down there as you need. So you could say what your as a peer on the network, you could say what your view into what the latest block is. You could just publish that on your identity, and others could, if you, for example, had a very resource-constrained device that you owned, you could tell it to just follow whatever you had published as the latest, or whatever the Ethereum Foundation had published, or N of M good actors, and then you have a very lightweight consensus sitting on top of the strong heavyweight consensus of a blockchain. But I mean, Ethereum already works, so why would you bother building all this? So one is IPFS and libp2p. It's more general. So I think you're going to have more people coming out of the woodwork to contribute new pieces of technology that maybe use Ethereum consensus here and use maybe state channels, or to be part of that peer-to-peer network it's a much more open invitation, I feel. Whereas messing with Ethereum protocols, you might get the cold shoulder a little bit. Hopefully that's not true. But anyways, I find it to be open by definition, and so I think that will encourage lots of people to play with it. But not only that, we need it at MetaMask. Currently, by default, when you use MetaMask, you get you can interact with Ethereum in your web browser, and Frankie's going to talk about that later. But you can see it's hopefully not bugging out right now. It's up here in the corner, and I can use that to interact with Ethereum. But the way we make that work without you sitting there syncing for minutes or hours or whatever it might be is by default we rely on a trusted data source, and so you still have trust agility. At any point you can say, no, I want to get that data from my own node, or I'm going to spin something up in the cloud, or I'd rather move to this other data provider. You can do that at any time. So so if we were to become bad actors suddenly, you could move off of that very easily. So that's quite valuable. But it's still, so we have a poor default. And so our hands are tied a little bit because we have no TCP UDP in the browser to talk to the main Ethereum network. So what are we going to do? Perhaps we'll build a second network on WebRTC via libp2p and using some bridge nodes to help make the data accessible and get transactions to the miners. Thanks.
All right. Well, next we have Why Are You Sleeping? And he's going to be giving us some DAG API cool blockchain integrations. So whenever you're ready, just go ahead and stick it on. All right. It's going to be interesting. Okay. Just put this here then. Cool. Yeah? Okay. Yeah. Actually, click that on the...
All right, so hi, I'm Y, and I'm not the presentation giving type, so I didn't make any slides like the previous two people had, but I've got some cool demos to show you that kind of hopefully demonstrate what these past two talks have been talking about. So to start off, I work on IPFS, and been recently doing a bunch of cool stuff with IPFS and IPLD and integrating different blockchain stuff. And I've been paying really close attention to Kumavis's interesting Ethereum stuff, and also been working on doing the same thing that he's been doing for Ethereum for Zcash and Bitcoin, which is great because they have pretty much the same exact format, so I don't have to write that much code. It's fantastic. So to start off, I've got this nice little. Is that big enough? Is that too big? Oh, crap. What did I do? I don't know. Oh well. It's gone. I've got this IPLD object, and this is a JSON representation of the format, which is not stored as JSON. It gets converted to CBOR, which is like some cool one-to-one mapping, but it's easy to write JSON. And it's, as you can see, it's just like a regular object, except for two interesting things here. This is an IPLD link, and so what that does is this object can point content addressingly to other objects. And I can do interesting. So what I can do is I can take this and I can ingest it into IPFS and get a little hash. Well, little is not quite what it is. And then I can get that back out if I can type really easily. Oh, and it's ugly. And it's basically the same thing, a little reordered because JavaScript doesn't care. And then I can do other things like walk paths on this. So I can say, /food gives me bar, or /baz gives me this array, and I can subscript that array to give an index, right? The other thing I can do is I can index this Batman array, right? Which now, oh my god, I broke something. Oh well. I can get this object. Oh my god, what is that? That is actually the JSON output of a picture stored in IPFS. So if we, instead of trying to get it as a DAG, we'd say, I just want that raw data. So I'm just going to cat this. And, woo, look at all that garbage. You know what's really cool? Is that can go, and it's a kitty. And then the other one, which I named quite well, is a badger. So like, the reason those are in there is I did IPFS add, and it gave me a hash, and I just took and put it in that object's links. So if we look back here, that is the hash of that cat, and that is the hash of that badger. And so you can build these objects, and you can design whatever data structure you want, and IPFS can walk through it and walk along it, and kind of like do cool things with it. And so this is just the CBOR IPLD DAG type stuff. So the cool stuff I've been working on that's more relevant to today is I've been working on this Bitcoin and Zcash stuff. And I'm just going to demo the Zcash stuff because I didn't feel like syncing the entire Bitcoin blockchain to my laptop. I don't have that much storage space. So I have this little IPLD object that has Zcash and a link. So I'm going to take this, and I'm going to put this into IPFS the same way. And grab this. And I'm not going to bother to output this. I'm just going to go straight for what it's linking to. And that's a lot of text. What we're seeing here is a Zcash block, a raw Zcash block. And it's actually not, the format is not changed at all. The format that IPFS is storing it as is the exact same bits as the Zcash block hash. So if we do, just to kind of further my point, so this is the hash of the Zcash block, right? Everybody knows, or hopefully people, kind of get like, so when you're mining a block in most blockchains, you're trying to find a block that has a bunch of zeros at the front. And so if you look at this hash, there's not a lot of zeros at the front. Well, the reason for that is because it's base 58. I took the Z off because that's telling me it's base 58. It's base 58. So let's convert it from base 58 to hex. Oh, whoops. Let me take a few things off. Hopefully this works. Oh, yeah, there's zeros at the end. Right? It's one at the end. So this is the Zcash block hash that was mined to have a bunch of zeros at the end. And so the data is exactly the same. It hashes to be the same thing, which I think is like really cool, which means we don't have to like rewrite the format. And I can do cool things like I want to access the difficulty of this block. Oops. God, I'm great at typing today. Difficulty of this block, since JSON mangles numbers, is some thing. Yeah, tell me about it. I can access the parent of this block. It's another block, a whole bunch of text. I can access the parent of the block. And guess what? The parent of the parent of the parent of the block. And even cooler, though, I mean, sure, you can walk the blockchain all the way back, and that's great. But where am I? I can access the transaction Merkle tree of this block. And this is a little weird. So when you look at the transaction Merkle tree, you're like, oh, it's a list of things. But no, it's not a list of things. It's actually a tree, and it's a binary tree. So the Merkle root in Bitcoin type blocks is the hash of the root of the tree. So when you get the hash of the root of the tree, you're going to get an array with two things in it, the left of the tree and the right of the tree. And so we can walk this down, say like the left of the tree, and that gives us the 0th block. And cool. Look, there's like inputs. Let me make that prettier. And so this is a transaction that we referenced through some path through IPFS. Has the exact same data as it would in the blockchain itself. And you can walk through this. You can get the values. You can get like, oh, look, this many 10 Zcash was sent to that address. 2.5 Zcash was sent to that address. This is the mining reward. And so you can go through and you can access any of these transactions, find the values, and operate on them. And this is really cool. I'm super excited about this. What I'm hoping to do with this is do things like, so here's the script, right? Who here knows about Bitcoin op returns and how it's a nasty, ugly hack to put data in transactions? Well, one thing I'm going to try to do is get an op return, get this to be able to follow links, like content address links that you store in the op return, which would be like /script, and we'd have to somehow figure out some format of that. But that's like the next step along this way, so that in the op return, I could put the hash of an Ethereum block in a Bitcoin or Zcash transaction, and you just walk through that chain. And that's probably one of the things I'm going to be working on this week during this hackathon is walking paths through blockchains, which is going to be cool. And I haven't written the Ethereum parsing code yet, but somebody in this room has already in JavaScript, so translating that to Go should be easy enough. And I'm really excited to see where this goes. So once you have this, you can do some cool stuff like, well, now all the data's here and it's accessible. What do you do with that? Well, I had somebody who writes JavaScript write me some JavaScript. Let's see, how do I move things around? So we wrote this little thing we call it the Zcash Explorer, and it's a static app that I'm going to hopefully demo. Not remembering how to do mirrored screens is very strange. Wow, that's big. Chrome, you can chill out. Oops. All right, so we're going to go to the hash that I just generated and shrink it down a little bit. So we have a Zcash Block Explorer. No, don't reset it to default. Go away. So what you can do is, this is just a nice little JSON, HTML representation of a block. I can walk back through the blocks, and I can just keep clicking, right? I can go to the transactions, and some of the transactions are weird because it doesn't there's a weird thing about the daemon where it if a transaction isn't interesting to you, for some reason it won't sync it to your computer. So I'm not entirely sure the problem there. It's behaving weirdly right now. Damn it, I wanted to demo that. But yeah, you can do cool things like this, and you can have a blockchain explorer like blockchain.info without a central server. You don't have to rely on somebody to be hosting this, a site to view static hash-linked data for you. You can just do it yourself and view it locally, which I think is really cool. Yeah, and that is about as much demo as I have right now. I hope that was filling enough time. Yeah? Cool. Thank you.
All right, next up we have Wanderer. And Wanderer works on the EVM, right? The Ethereum Virtual Machine, right? And yeah, so this is a nice little grab bag talk, so should be fun. So go ahead and put that on.
Oh, okay.
Yeah. Anywhere you
Whoa.
Yeah, I need help.
I have to push a button or something? Okay, that's it.
Where did the mouse go? Here it is. Oh, I see what happens.
Yay. Yeah, hey, I'm Martin Beasy. I work for the Ethereum Foundation. I do research. I'm working on doing a lot with the Ethereum Virtual Machine right now. I'm wandering on GitHub. Today I'm going to talk about like really a dag of ideas because they're not ordered in any. They're partially ordered. Okay. So yeah, what would it look like to have an interplanetary operating system? We have file systems. Oh, yeah. Why not? And this also intersects a lot with the work I'm doing, and yeah, I think it's really cool. So let's start with here's where we're at today. Like we can mount a IPFS hash. We can at the root directory, and you can CD into any hash, and then below that are all the files, and that's pretty cool. So next step is obviously running binaries from a mounted folder. So I should be able to add my bin directory and CD into the hash and run a program. Now, this doesn't quite work right now. I think that's maybe due to the limitations of Fuse, but you can't actually make a program executable. But I'm sure it's just a detail. So the next thing we'd like to be able to do is write files. We can't do this yet, as far as I know. Maybe, I don't know if y'all figured it out, but writing is a little bit more complicated. So but it's pretty important for operating systems to be able to write files. But it doesn't quite fit into the way that IPFS currently mounts files. Right? So you mount the root directory, and you have the hashes directory, and then all the other files. So if you change a file in one of the directory, obviously you're generating a new root hash. So where is that hash? So there has to be a slightly different topology. So maybe one way to do it would be to mount individual files or individual root hashes. So for example, maybe I could mount a root hash directly to my music folder, and that would contain all my music. And then I could CD into it, download some music, but we have a new hash there. We have a new root hash since we changed it. So we need some utilities. Unix and Linux has print work directory. This is actually most of the time implemented in your shell. It's not implemented as a user space program necessarily, but it's always built off POSIX functions, get current working directory or get present directory. So ideally we would have maybe something like print working hash, print working directory hash. to get the current root hash. And there needs to be something equivalent to a POSIX function where we can build user space programs to do this. Now, it doesn't have to be a POSIX use function. It could be RPC calls or something, but we need some layer where we can build user space utils like that, I think. And we should also be able to do the same with IPNS. So, like, if I mount an IPNS directory, this is I think really cool. Like, if I have just a public key, I can mount it and get all updates. I can I can mount Movis's music file to my music directory and get all the new music files he puts in there. But if I have the private key, that should mount as not only readable but writable. And then whenever I write to that directory or change it, the new state root gets published. So, and then we should be able to have like fine-grained controls over sharing subgraphs. Like I should be able to CD into my music folder, create a new IPNS link to it. So that creates a new private public key pair, and I can give that hash out to someone. I should be able to do it again. So I create one, I should be able to create another one. I should be able to list out the different links I have to a particular folder. And lastly, I should be able to revoke them and remove those links. And this enables me to have fine-tuned control over who has read permissions to what folders. And I think of it in terms of capabilities. I don't know if anyone's familiar with capability systems, but cool. One person, 2, 3. Oh, that's pretty good. But a IPNS link is a read capability, and after you revoke it, obviously the person still can always read the last hash that was published to it, but they won't get any further updates. So yeah, multiple IPNS identities would be like super awesome, and being able to bind them to folders. So one thing that'd be cool would be like to have link all my friends' music together in a local folder. You know, like I link this IPNS hash to friend/Brad. I could have all my friends' music in a folder. I don't know. I like music, so I think it's cool. And the operating system, so IPFS doesn't traverse through IPNS links because that's mutable, but the OS system layer should be able to traverse through IPFS links and IPNS links and any other kind of links that we throw at it, not just Merkle links. We also need to be able to have, so this gets into the point, we need flexible link handlers. So let's say we have a scenario where the music folder is shared on IPFS, but we have a subfolder that we don't want to share. So we need a way to accommodate that. So maybe what gets hashed into the music folder is just some symbolic reference to this thing here, but not the Merkle link. So as I said, this is an unordered speech. It's a DAG. So I'm going to switch gears. I'm doing a lot of work with WebAssembly right now. And I want to talk about, 1 second, WebAssembly is a new portable, sized, and load time efficient binary format that aims to execute at native speed by taking advantage of common hardware capabilities across a wide range of platforms. I think it's really awesome. The key takeaways are fast, efficient, it's secure, sandboxed, has toolchain compatibility. It means it works with LLVM. So anything you can compile with LLVM, you should be able to run in a WebAssembly virtual machine. So out of the box, C, C++, Rust, all those things work. And it's extensible. It's easy to plug it into other systems. It's easy to embed. And it has the combined powers of the web. So yeah, it's being standardized by Google, Microsoft, Mozilla, Apple. So that's, yeah, all the big players. In the history of it, it came out of something that was written in 2012 called the Extensible Web Manifesto. And the problem that the web had was, and still does to some extent, is whenever it adds a new API that extends the surface area, that needs to be secure. So instead of having a large surface area, if you build small primitives, and then you can build your new features in these low-level primitives. So yeah, another thing would reduce the growth of complexity and therefore bugs in implementations, and allow browsers and vendors to iterate on libraries before publishing high-level APIs, right? And in Ethereum, all these things are also applicable to blockchains. Actually, even more so, right? So, like, what we face today is we have a really large trusted computing base. We have a virtual machine. We have all these precompileds, and we have like state rules. And state rules are like how we update the state, like moving balances from one count to another. And I would say it's even getting worse because we have more precompileds coming down the line, and every time we add a precompile, we have expanded trusted computing base. And it's super important in a blockchain that like every implementation implements it correctly. If you don't, you break consensus. So it's even more important than in the browser environment. So a big trusted computing base is really bad for symmetric computation platforms. And that symmetric computation is the basis for, as far as I know, all blockchain-based consensus. So instead of building things out, we should start with a very small trusted computing base and have a VM bedrock and then build everything in it. And I think we should think about the state rules more in terms of a kernel, since ultimately they deal with inter-process communication between contracts. It really is a kernel. And then like all the precompileds should just be user space contracts like any other unprivileged contract. And this is, I'm experimenting with some of these ideas in eWASM kernel today, and part of the eWASM project. So now to jump back, we have an IPLD, as Juan talked about earlier, translators. And I was super excited when he said that they were thinking about using WASM, because that's what I'm talking about too. So a translator, so there's a little bit of a historical context to translators, and I think, IPLD matches closely to what translators are. Translators in Plan 9 and HERD. I don't know if anyone knows anyone know what Plan 9 and HERD are, right? Okay, there's a few. Yay. So they're operating systems. Plan 9 was developed as a sort of to be the successor to Linux or Unix, and didn't really take off ground for a number of reasons. One of them was licensing, and HERD is also along the same lines. It's an operating system that Richard Stallman's been developing since like forever. So, anyways, a translator is a normal program that acts as an object server and participates in HERD's distributed file system. And basically what it does is takes in some data, it goes to the translator, and exports a common file system interface. And something like IPFS or IPLD, you take in some data, you put it through a resolver, or translator here, and you come out with a common vertex. So another way to put it is, this is also copied out of HERD's manual. Translator just translates from one representation of data structure into another representation. So pretty straightforward. So yeah, if you wrote IPLD translators in WASM, you'd only have to implement one translator for all implementations. Translators themselves can be resolved by IPFS, which means less dependence on implementations and more modularity overall, which is great stuff. And you could implement it, these things could be implemented in user space, ideally, if there was just a common, API. So, one thing we do with translators that Kamavis has been working on, it's super cool, and also Why Are You Sleeping with other blockchains, is importing the blockchain into IPFS. So, like, this isn't actually the structure of what Ethereum looks like totally. I left out a lot of stuff, but this is an example of what it'd look like. So you have a block at the top level of accounts, and you have all your different account addresses, and then inside account you have a nonce, a balance, and storage, and inside storage you have all your different keys. We have this file structure now. What if Ethereum contracts were just programs in a general purpose OS backed by a content addressable file system? It's sort of a mouthful, but like that would be pretty cool, I think. So what do we want from user space? Well, we know we need to run symmetric computations. So I'm starting from Ethereum, trying to work backwards from what we want. We have Ethereum, we have a content addressable file system, so let's try to work backwards. We know we need symmetric computation. It needs to be deterministic by default. It needs to be sandboxed. Right? And I think it's pretty important that we can reuse legacy programs written in C and C++. And it also needs to be fairly simple and well specified. And several of these things are covered by default by what WASM does. But we need a communication layer still. We can't just use Linux straight because it's very complicated. There's lots of details we don't care about at this layer. It's not completely deterministic. It's not sandboxed by default, though there's some interesting work going on with Subgraph and Qubes OS with regards to sandboxing. Okay, so jumping a little bit again, and we're going to come back. It will make sense. Actor model. Actor models is really cool. Actors are these little programs that run, and they get messages in their mailbox. And when they get the messages in the mailbox, they respond and process the message, and they can spin up the other actors, and they can send messages to other actors via channels. Right? So I think that each contract or program is an actor or server running in a microkernel framework, right? And the reason the actor model is really nice in this environment is because each actor is a natural spot to build the sandbox around. Really quick, bigraphs. This is sort of my bedrock that I think of everything in. So actors and the channels they communicate through would be the hypergraph on the left, which is a link graph, and the Merkle-Deg structure is a place graph represented by this forest here. So it's not really important that you need to know this, but there's a solid mathematical framework underlining this. And I think it's good to have sort of a bedrock reality or bedrock model reality is so that which you can use to describe higher level features. So here, the forest or place graph is the Merkle-Deg, and the hypergraph is the communication lines between programs. So, for example, we saw earlier that the big graph of Ethereum mapped into a folder or DAG structure. Here's it sort of graphed in a hypergraph. So blocks at the top, and then all your accounts, and then you have one account here, and maybe your TXs. But let's say like the account code wants to figure out the current block hash or the block number, or block difficulty. It may want to talk directly to the block, so it may open a channel to the block. So it's the DAG structure and the actor channel in one graph. Microkernels. Microkernels have a long history. There's lots of them out there. But so what they are, if you're not familiar with them, it's just a very minimal amount of software needed to provide or to implement an operating system. So the microkernel that we're working on or thinking about is just providing inter-process communication between our actors, which are Ethereum contracts. So here's where we are today. We have all these things squished together into one protocol, one software stack, consensus, contract, IPC, networking. Sort of big ball of mud, scary. Here's where I think we should be moving. So at the bottom, we have a file system. Networking could be provided by IPFS and libp2p. On top of that, we have a microkernel, which our programs and contracts exist in. And from that, we can build consensus protocols, such as Ethereum. And, as the ecosystem grows and progresses, this is not fixed. We can move more and more into the microkernel layers, and more can just become user space programs. So yeah, modularity is really important. Conway's law. An organization with design systems are constrained to produce designs which are copies of the communication structures of these organizations. Basically, if you hire 7 teams to design a compiler, you're going to come up with a compiler with 7 different modules or 7 different steps. So it's and systems have to, I think, be modular for them to evolve, because that's how humans program and work together. So I think it's really, really important to break things off into modules. So vertices. Vertices are programs. Linux has a saying, everything's a file. And our IPOS, everything's a vertex. Okay? And to borrow from Plan 9 again, they just have servers that just a user space program can implement a file server. And one possibility to use these servers for is to synthesize vertices, or files, on demand, perhaps based on the information on the data structure inside the kernel itself. So you have maybe a DAG, and you would have a agent, our actor, and it could synthesize a further DAG depending on its position in the tree, etc. So it'd be nice to do stuff like that. Everything's a file. So I want to make a small note that vertexes are a little bit different than files, because a vertex has a value and it has edges. If we say a vertex is also a program, that value is code. Those edges are ports. So in actor terminology, ports are what actors use to talk to other actors through. So we need a system API. And it should be super simple. It needs to be easy to specify. Everything needs to have a very small trusted computing base here. And there's only really 2 things we need to do. We need to interact with the ports, send messages and whatnot. So set and get ports, send messages, whatnot. And we need to store and retrieve values. from the file system, which is the Merkle DAG here. So this is sort of what I'm playing with also with eWasm kernel, seeing how small of a API we can get it down to. And we need the core of it's really inter-process communication. So channels are lines of communication. Ports are the internal name for that channel for each program has. Ports can be duplex, read-only, write-only. Ports are capabilities. Well, they actually have two capabilities, a read capability, write capability. Those capabilities are delegatable, so you can send them to another actor, which means you can send ports around, which is pretty cool. So that's actually how, back in my early example where the contract talks to the block, to establish that, actually you'd have to send a read capability down through the Merkle DAG hierarchy till it gets to the actor. So also, by the way, a Merkle link is read-only capability. If you want to know more about capabilities, you can see capillor.com and ewrites.org. So messages here are, we need atomic messages and non-atomic messages. Unfortunately, we have to support atomic messages right now. Non-atomic messages, Ethereum doesn't have any notion of non-atomic notions at the moment. But it will inevitably rise if we ever have sharding. When we have sharding, it's needed for any type of scalability, really. Messages are unforgeable. They have a from and a to that's set by the operating system, and they have an immutable payload. So that's what I'm using for messages right now. Super simple. And where do I think this is all going? Is like we're you've all seen the Moore's Law graphs, right? Where computation is like doubling, or not computation, speed. And we all know Moore's Law is sort of like ended, but we still see this exponential growth in technology, and we still see a really good growth of computing power per watts, right? So we're doing more computing power for less energy. And I think the net result of this is going to be that we push our computation out to the edges. Right? Instead of having it in big data centers, we're going to have, well, the Internet of Things, but more and more and more. We'll just see computation happening all around us. This is called ubiquitous systems. Well, it was called ubiquitous systems. But now it's called Internet of Things, I guess, or something like that. So Robin Miller talked about this in like the 90s. He said such a system or its component agents will be self-aware, possess beliefs about their environment, possess goals, enter into and achieve goals, and be able to adapt and to change circumstances without human intervention. So computations are made to appear anywhere and at any time and everywhere. So, they're omnipresent. We're pushing computation to the edges. And I think the way that we're going to interface with these ubiquitous systems is through a homogeneous operating system, not necessarily a singleton, right? A content addressable file system really lays the groundwork for that, because you don't need a central server. You can have a lot of edge nodes to be able to retrieve your data, right? And from that, you can build, an operating system. So I think this will look a lot like my web browser with a lot of tabs open. Web browsers actually do quite a bit of this, right? They have sandbox processes. They have inter-process communications. Web workers are agents. They're modeled after the agent model. Actor model. And the web is, it's mobile code. So I think there's a nexus between where web technology is taking us and decentralized technology is taking us. And I think it's really important to work along with web technology and the huge, massive web community that we have. So how to get there? Be practical over perfect. Like, you can stare at this. There's a lot of theory, right? You can stare at this theory all day long. But for me, I think, and for a lot of people, just like writing stuff, figuring out what happens in the real world, and then feeding back and looking at the theory and moving forwards is the best way to go. So don't worry about being perfect. Just try to be practical. And embrace iteration. Everything's a prototype. Like, don't get caught up in like, building the big final shiny thing. It's just one iteration. Keep it modular and follow the Unix philosophy. Right? Really quick note, Plan 9 was awesome. But Linux really got one thing right, modularity. And so Plan 9 had all these cool things about it. But it turns out what really matters is modularity. And Linux was the first one to get that modularity down, and that's, I think, one reason is like nothing has been able to beat it. Lastly, be your own core devs. Like, write your own code. If you see a need, it's your job to fix it. So, yeah, that's all I have to say. Oh. Okay.
And Frankie, you're going next after Andy?
Yeah, I guess so.
We got time. All right. All right, next up we have AP Milan with DApp Hub. That builds some pretty great dev tools for decentralized technologies. So go ahead and let's drop that on.
Like there?
Yeah, yeah.
Howdy.
Good luck.
Thanks. So hi, my name's Andy Millennius, and I'm here to talk about DApp Hub. DApp Hub is a blockchain answer engine. I don't know why test is in there. But before I talk about DApp Hub, I'm going to talk about where we've been for the last year. If you've heard of us before, you've probably heard of DAPL, which is our command line multi-tool for working with the Ethereum blockchain and other EVM-style blockchains. Right now, it's a very it's not very opinionated, but we still think it's a bit monolithic. It's very large. If you follow the updates, we haven't pushed many updates recently, and that's because we're in the process of splitting out all of DAPL's features into new, smaller applications. So we've already taken DAPL's most popular feature, the native Solidity unit testing, and we've split it out into a Rust-based unit test runner that's much faster called DAPL Quick Test. We're going to do the same thing with the native Solidity blockchain scripting that we do. And we are going to update the JavaScript package to have ERC 190 support. That's Ethereum package management. We love ERC 190. But then that'll probably be where we feature freeze it. And so from there, look out for other applications that we're going to be releasing under the DAPL name. And the next thing that we've been doing is hardening and expanding DAppSys. So DAppSys, the reason that we're sort of shifting focus away from DAPL a little bit is because we are very much a smart contracts shop. We have a lot of generic smart contracts now that are available for developers to use. And so if you, during this hackathon, decide that you want to use smart contracts, we may have
like a generic solution for you, so you don't have to rewrite code. So there's definitely too much to talk about here, but the one that I do want to highlight is over here on the left. dapsys is particularly good at access control. And if there's one pattern that I can't recommend enough from dapsys, it's definitely the DS auth pattern. Any package, any smart contract that you want to be like owned by an authority, you make it of type DS auth, or you make it inherit from DS auth. Then you can make a DS authority object. We've got like 2 examples down there. And the DS authority object can own these large smart contract systems, and it makes it a lot easier to upgrade them. It makes it very easy to create upgradable systems, which is really, really important. So definitely look into this. And the last thing that we've been up to lately is DAPHub Companion. DAPHub Companion, as you can see by the little bar in the middle there, is a Chrome developer tool. So it exists in the Chrome developer dashboard. Right now, the state that it's at is it's sort of ready for pre-alpha internal testing. What that means is if you want to try it out this week at the hackathon, just come and find me and we can get it set up and you can start using it yourself. And so it does 3 things right now. The first one that it does is it's got a little Web3 sniffer. So you can see calls that are going to MetaMask or to your local node. The next thing that it does, as you can see down here, see these contract names. So what it's doing is it's reading either the ERC-190 registry that's been set up, or when you publish things to the blockchain using DAPL, you push your data to our servers, and it displays ABIs and stuff. So it's like a universal smart contracts interface for any website. You can go to any website, open this up, and you can see all of the smart contracts that Web3 is talking to, and you can interact with them, trigger calls, and stuff like that. And so those 2 things are cool, but probably not enough to be like super productive. It's a little bit more gimmicky. It gets really, really useful when you get to the 3rd feature, which is blockchain forking. What this allows you to do is, at any time, fork the Ethereum blockchain into a private replica and use it against your UI from the Chrome developer tool. So you can basically create a fork, test a bunch of transactions. You can also do address faking. So you can pretend to be another actor. You can do really fancy things like integration tests, like full feature tests. And so the blockchain forking aspect is the one that we're most excited about. And we think it's going to get really, really interesting when we incorporate Remix, which is the Ethereum debugger. So we're already talking to the Ethereum Foundation right now. They know about DAPHub Companion. They like it a lot. They want to support us in getting Remix into it. And so what that'll allow you to do is fork the blockchain, run a test transaction, and then step through the Solidity line by line, which is something that everybody's been waiting for forever. So get excited for this. This is coming really soon. It's pretty much ready. And like I said, if you want to try it out this week, then just let me know. So DAPHub Companion is cool, but we at this, part of what I'm talking about in this speech right now is what we're doing at this hackathon. So what we want to do at this hackathon is we want to develop the MVP of DAPHub Core, like the home base. This is cool as an extension, but you need like a website, I think, to go to do some of these things and a lot more. And so that's what we're going to be working on at this hackathon. And so I'm going to go over a few of the features of what daphub.com is going to, where it's going to draw from and what it's going to do. And so the best way to describe it, I think, is the tools that have inspired us and the tools that we want to, like I said, draw inspiration from when we build DAPHub. And so the first one are terminal-style web tools. The ones that you'll be most familiar with are Rocket Chat and Slack. But it's basically any web tool that is dominated by one text input box, and then the user uses like commands, either structured or otherwise, to create effects in the environment. In this case, the environment is a shared social space, but you can do all kinds of crazy things like invite, expand, blah, 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 all those things right there. And the idea of all of your interaction with the blockchain being like dominated by like one input box in a terminal style, I think can unlock a lot of usability because there's so many different things that you can do with a blockchain. It's just like with a terminal, there's no way that we could create the perfect UI that encompasses every single possible thing you can do. So that's why we want to make like a generic experience. And if you look here, like specifically chat is interesting because another thing that inspires us is natural language processing. So the idea of like conversationally working with the blockchain is exciting to us as well. This is something that I think Google has pioneered. I think Google, part of the reason that they won the search engine wars is because they kind of took a terminal-style approach to exploring the web. It's just like an input box, and then you figure out what you want to do, and then boom, there's your answers. And they've taken it a step farther now, where it's much more conversational, and it's structured in a way where the query is almost like emergent. You don't really need to know how it works. And so that's something that, while it may not, we may not be able to support it this week during the hackathon, that's something that we want to bring to DAPHub. Wolfram Alpha. If you've used Wolfram Alpha, that's a big inspiration for what we're trying to do. We're kind of trying to make Wolfram Alpha for blockchains, you could think, if there's any takeaway from this. And another one that is interesting is REPL-style web tools. So I'm sure many of you have used browser Solidity before. Browser Solidity is awesome. Another one for Python is called Jupyter. So we think this is really cool. As soon as you create like a terminal-style developer tool, obviously everybody's going to want to know about text editors. So we think that the idea of being able to pop up a very minimal but very rich programming environment where you can have like all sorts of cool JavaScript tools like loaded in the context, like ETH deploy and ETH.js and Web3 and Dapple's tools as well, and all sorts of different things. Like we like the idea of being able to just jump right into it in the web experience. Like if you've ever used Jupyter, or I mean it's the same thing with browser Solidity, you just go from not working to suddenly I'm like programming in this environment instantly. And so we think that that could add a lot of accessibility to working with decentralized technologies. The next one are data transfer protocols like IPFS and Swarm. I think that it'll be really cool to explore these networks, and all of the stuff I'm hearing about IPLD is obviously super exciting. That would be really fun to support to get to during this hackathon. Additionally, application-specific protocols like the Ethereum Package Manager. We are going to go crazy on the Ethereum Package Manager. In fact, like DAPHub, the idea is like, I would say over a year and a half old, and it got stalled on the Ethereum Package Manager. We couldn't like figure out the protocol correctly, and that's sort of what stalled it. But now that it's ready and it's out there, like we are just so excited. I'm serious. The Ethereum name service, media chain, so like tying together different elements from different networks. But we want you to be able to explore all these in a really, really like rich way. And then last one, sort of tying into using other networks, is something that inspires us. Definitely not going to get into this hackathon, but something that really inspires us and something that we really want to support in DAPHub is this idea of automated DevOps orchestrators. So the most famous one is probably Chef. AWS has a few as well. But the two that inspire us the most are SaltStack and Ansible. They take like a lot more of a decentralized approach to DevOps orchestration. And so something that we want to bring to the blockchain is the idea of, so this is an Ansible playbook right here. It's written in a very declarative style. You sort of say, you know, I want an Apache web server. These are my hosts that I want it on. This is the user that you're going to sign in as. First do that. That's the way that you're going to do it. Then do that. That's the way that you're going to do it. You just kind of state your desired end result, and then Ansible just like SSHs in and does it all, and it does it idempotently. So you don't have to like, it doesn't matter how many times you set it to it. It just makes sure that the end state looks like this. And so part of the problem of what makes Ethereum difficult to work with today from the user's perspective, I think, especially people that are involved in decentralized communities, is that it's very difficult to ramp up usage of traditional web server technology, like traditional Web 2.0 technology. One of DAPHub's biggest contracts is working with MakerDAO, and the process of managing all of the DevOps stuff that MakerDAO requires is very messy, very disconnected right now, and most importantly, there is no auditability on behalf of the people who are involved in the community. So that's something that we think will be really exciting if we can get like a a very high quality experience there. So now I'm going to show you a couple of test screenshots. What we're going to be trying to do for this hackathon is create a MVP that targets the use case of MakerDAO, because we work with them so closely and we understand their use case really, really well. And most importantly, all of the UI I'm going to show you already exists as Maker websites. So it'll be like a little bit easier to incorporate it into our website. But the experience with DAppHub, like I said, should be dominated by a text input box. You can do anything from this text input box. So to give you an example, if you want the MKR chart from a decentralized market for the revenue and the profit over the last 24 hours, you just type it in, and then boom, it pops up. You can imagine there's a link to this. You can share it with your friends. You could have it show up on your homepage every time you go. It's sort of like your experience. Another one is voting, of course. What is Ethereum if not a voting machine, you know? So we've got a proposal here, the amount that has voted, the amount that is needed to approve, the amount that you have to vote. It's very simple. It's generic. It seems boring, but like the stuff that everybody is going to use is just like super generic like this, you know? So we want to just support everyone's use case at once through this answer engine. And then the last one, this is the one that I'm most excited about, is visualizing smart contract systems. So that is a goofy low-resolution picture of the MakerDAO smart contract system that is up right now. And so the idea of being able to get a bird's-eye view of these smart contract systems and seeing like all of the different functions and who can talk to who, all of the landscape of the authority is exciting as well. And so we think that will make it a little bit easier to kind of wrap your head around what is going on in these systems. And so, like I said, these are 3 websites that we already have running for Maker right now. So a lot of what we're going to be doing is just building the infrastructure around them and supporting this experience in one unified sort of place. So yeah, that's what we're going to be working on this week. If you're interested, come say hello to me, or you can find me on our chat, dapphub.chat. Oh, and I'm going to do a little prototype demo also. So we made like a really low-key prototype. We're not going to use any of this code because we decided to switch to Elm. But I'm going to show you anyway because it kind of gives you the idea. And the reason that I'm showing you is that in those pictures, it doesn't really convey, I think, what you can do when you pull up like multiple cards. So like this is one, right? Like suppose you put in a hash, you get all the hash information, no surprises there. But then suppose, oops, underneath, I want to create an editor. Now you see it's like, this doesn't go away. This is like what I was saying with like the terminal experience. You know, your history stays there. And so now I've got this little terminal, and it's kind of optimized for coding and stuff. And you can see that like these are 2 different experiences, but like unified together into one website, just like a terminal. So now I'm done. Now you can clap.
All right. And then last, but definitely not least, Frankie. What are you going to be talking about? Go for it.
Where did the thing? Okay, so I'm not going to talk too long about MetaMask because we're a little short on time and there was a lot, and I just don't want you guys to have time to ask all the other speakers questions. So, what is MetaMask? MetaMask is a Chrome extension that ejects the Ethereum network into the browser. Put simply, what does that mean? This means you can build web applications that use the Ethereum network. Next slide. How do I do that? Looks a little something like this. I'm sorry, I couldn't get the colors up there. I know some people out there probably hate me right now. But what I really want to show you is that I have a hard time figuring out how to get out of full screen every single time. So a prettier version is in our MetaMask FAQ. For those of you participating in the hackathon, you're going to want to go to the MetaMask compatibility guide for developers, and that one's actually in color. But what does it actually mean to have the Ethereum network in the browser? I can show you what that means. So I'm sure you've seen that fox before. If I lock that back up, I have a fox. This is MetaMask. I enter my password. And this is if I've obviously already created an account. There are some really amazing videos voiced over by one of my teammates, Dan, who was working the camera, who was super awesome. Again, short on time, sorry. Here's some history of transactions. It looks really simple. We're not really trying to do anything fancy here. I personally think it's beautiful and is awesome. But let me show you where the real magic happens. If I go in here and I type window.web3, I'm going to get an object. Now, if I go up, and I think I still have it in history, oh, look, web3.eth.7 transaction. Sure, why not? Look at that. MetaMask is going to pop up a little pop-up, get the user confirmation, and hit accept. Callback happens. It's going to say null. It's going to give you the hash of the transaction. You do whatever you want with that. You're the dApp developer, you know. But it's that simple. And there's some fun little nifty things like, oh, hey, I have this address here. This is my MetaMask account. Well, you as the dApp developer have access to that. You can go like web3.eth, yeah, eth.default. Every time. It's always the number. .eth.default account. And look at that. That's your MetaMask account right there in the browser. Woo! Okay. That's about as much as I wanted to show you guys. Oh, yeah. You know what? We get to talk to a lot of dApp developers, and they come to us with help and all these things. They also come and submit our dApps. So let's see it in the wild. I love this. This is my favorite way to QA, guys, just by the way. It's going to yell at me in 2 seconds. Wrong network. Really simple. We start off with the Robson test network, just as a reminder that we are beta, and can't even turn it down. So, main Ethereum network, hit OK. It's going to reload. Please wait. I'm going to press play and enter my password. Accept it. I'm playing a game. Woo! I'll try not to space out too much on the game while I talk to you, but these guys are really great. They store your scores on the blockchain, and if you are in the top 69 scores, you get a piece of the jackpot. Look at that.
They store your attempts on IPFS too.
Oh, do they? I didn't even know that. That's pretty cool.
Yeah. They only publish the hash of your attempt.
I'm not even trying to sell this game. I just you know what? If you looked at my browser history, it's a little more embarrassing, but I like these kinds of games, you know?
Ooh, I haven't seen a skull.
The skulls are crazy. Don't touch the skulls, man. Yeah. I swear to God, I'm going to stop. Anytime now. Anytime. Woo! Okay. I'll stop now. That is MetaMask. Please hang out, walk around. We're supposed to be out of here by 9. For those of you who hang out past 9, we will drag you to the bar, I think. No promises.
It's across the street.
It's across the street.
So one more note, you may have heard that we're calling this a hackathon, but we're about to leave. Because these are somewhat complicated projects. If you want to participate in the hackathon, it's over the week at your own house or at the local cafe or something like this.
Oh, wait, I've got the information for that.
Please. We're going to have a drop-in help day
On Wednesday.
down in Columbia City at the Seattle Bouldering Project. Because they have a nice cafe and you can also climb their walls. And yeah, so we'll be on IRC, Slack, Gitter.
I won't be
lots
on
of different
IRC.
things. And so, yeah, if you are going to participate in the hackathon, please.
Open an issue on the repo. It's already like, I've got a template on there. It tells you everything you need to do. Just follow the instructions, but open an issue on the repo. You don't even have to submit any work until Friday. Issues will close at 1. No one will be able to submit after that. You know,
And then we'll have 3 teams of judges choose the winner of the hackathon, and the winner of the hackathon will be interviewed by the Ethereum Review podcast, and you could pitch the rest of the Ethereum community on your cool stuff. Pretty much anything is in scope that's decentralized, so you can do whatever you want.
People have video streams for different people. It's like a video chat room.
A video chat room.
we call that Hangouts.
Google Hangouts.
Yeah, but something like more present footage.
We may figure, this hackathon is a living document, so
Yeah,
things
so
can easily change.
github.com/MetaMask, and you'll find the IPFS Ethereum Hackathon repo on there. And then you can find more information there. So thanks everyone for coming, and thanks to all the speakers, and again Galvanize for giving us the space.
Chat, what do you think?